Depth-first search, DFS, is one of the most fundamental graph and tree traversal algorithms in computer science. Known for its deep exploration strategy and its ability to traverse complex structures efficiently. Unlike breadth-first search, which processes nodes level by level, DFS explores as far as possible along a branch before backtracking, making it ideal for problems that require exhaustive search, path exploration, or structural analysis. DFS begins at a source node and moves to an unvisited adjacent node, continuing this process until it reaches a node with no unvisited neighbors. At that point, it backtracks to the most recent node with unvisited neighbors and continues the process until all reachable nodes have been visited. This deep-first approach can be implemented either recursively, which naturally mirrors the hierarchical nature of graphs and trees, or iteratively using a stack, which explicitly manages the order of node exploration. DFS is widely used in many applications, including detecting cycles in graphs, finding connected components, performing topological sorting, and exploring solution spaces in problems such as puzzles, mazes, and combinatorial searches. In tree data structures, DFS is the foundation for the well-known traversals, pre-order, in-order, and post-order, each of which defines when the root is visited relative to its children. In graphs, DFS is more general because graphs may contain cycles. Therefore, it is essential to mark nodes as visited to prevent infinite loops. The time complexity of DFS is O(V plus E), where V is the number of vertices and E is the number of edges, making it efficient even for large sparse graphs. One of the most important uses of DFS is in cycle detection. In an undirected graph, DFS can detect cycles by checking for back edges to previously visited nodes that are not immediate parents. In directed graphs, DFS classifies edges into tree edges, back edges, forward edges, and cross edges, enabling the algorithm to identify cycles through the presence of back edges. This classification also enables DFS to play a central role in topological sorting, where nodes of a directed acyclic graph, DAG, are ordered so that every directed edge, U(V), leads from earlier to later in the ordering. DFS accomplishes this by pushing nodes onto a stack after all their descendants have been visited, resulting in a reverse postorder list that forms a valid topological sort. DFS is also crucial in constructing spanning trees. When applied to a connected graph, DFS produces a DFS tree that captures the structure of exploration. This spanning tree reflects the deep-first nature of the algorithm, producing long, narrow exploration paths instead of the breadth-oriented layers produced by BFS. In addition to structural applications, DFS is valuable in searching problem spaces, especially in artificial intelligence and optimization problems. Many recursive algorithms, such as solving the n-queens problem, generating permutations or combinations, and exploring all possible states in backtracking algorithms, are built on DFS. In such problems, DFS explores options deeply, backtracking when constraints fail, making it the backbone of systematic search techniques. Another prominent application of DFS is in maze solving. DFS naturally explores a path until no progress is possible, then backtracks to try alternative routes. While this may not yield the shortest path, it is simple, memory efficient, and guarantees discovery if a path exists. Furthermore, DFS is essential in network analysis. For example, identifying connected components in undirected graphs relies heavily on DFS. Each DFS run labels one connected component, and repeated DFS calls identify all components. In directed graphs, DFS underlies algorithms like Kossarigu's and Tarjan's algorithms for computing strongly connected components, SCCs, which play an important role in optimizing compilers, deadlock detection, and analyzing dependencies. DFS is equally important in articulation point and bridge detection, which identify nodes and edges whose removal disconnects a graph. Key operations in designing robust networks. DFS relays invaluable information for these algorithms by recording discovery times, low link values, and parent-child relationships during traversal. In terms of space complexity, DFS is often more memory efficient than BFS, especially in wide graphs, because DFS only needs to store nodes along the current path. Its space complexity is O(h), where h is the maximum depth of recursion or the stack, making it particularly suitable for deep but narrow structures. However, DFS can be problematic in extremely deep graphs due to recursion depth limits, though iterative implementations using stacks avoid this issue. DFS also plays a significant role in solving constraint satisfaction problems backtracking, which systematically explores and prunes search spaces, is effectively a specialized DFS. Algorithms used in Sudoku solving, graph coloring, constraint propagation, and logical inference rely on DFS-style recursive exploration. In parsing and compilers, DFS is used to traverse abstract syntax trees, check grammar rules, and generate intermediate code. Another important property of DFS is its ability to classify edges, establishing temporal relationships between nodes through discovery and finishing times. These timestamps help analyze graph structure, detect ancestor-descendant relationships, and solve problems related to graph ordering. DFS also facilitates detecting articulation points and bridges using low values, identifying critical infrastructures in networks where failure would severely impact connectivity. In artificial intelligence, DFS variants such as iterative deepening depth-first search, IDDFS, combine the low memory usage of DFS with the completeness of BFS. IDDFS repeatedly performs DFS to progressively deeper limits, ensuring optimal solutions when depth is unknown but uniform cost is assumed. DFS is also foundational to algorithms used in game trees, where it explores possible moves in games like chess or tic-tac-toe, analyzing future states recursively. Although DFS may not always find the shortest solution, its low memory and ability to prune branches through heuristics make it popular for exploring large search spaces. In summary, depth-first search is a powerful, versatile, and deeply influential algorithm used across virtually every domain of computer science. Its recursive structure, low memory usage, suitability for exhaustive search, and ability to reveal structural properties make it essential for solving a wide range of computational problems, whether being used to detect cycles, generate topological orders, explore mazes, compute connected components, solve backtracking problems, analyze networks, or traverse trees. DFS remains one of the most important tools in algorithm design. Its ability to explore deeply, uncover detailed structural information, and serve as the backbone for more advanced algorithms underscores its enduring significance.